Thank you. Hello. Is this thing on? Can you hear me? Fantastic. So, my name is Piotr, and I'm a research scientist at DeepMind. 2 years ago, I've met here a lot of very friendly people. It's great to see. Thank you much for the invitation to come here. It's great to see friendly faces. And people ask me, so what kind of things am I working on at DeepMind? Am I even allowed to talk about it? Yes, of course. I mean, it just needs to be published first. So this is going to be the story of my life. Well, at least for the last 4 years. It will be 5 papers, all centered around the topic of navigation. And obviously, because it's at DeepMind, we only know one algorithm. It's called deep reinforcement learning. And we just work on this intensively as much as we can. Well, it's actually not true. We know other ones. Loic is going to tell you something more about other ones. But deep reinforcement learning is the foundation for this work on navigation. And navigation is a faculty that has been acquired by animals and many species of animals and humans alike, of being able to situate themselves where they are at a given moment, and how do they get to where they want to go? What is the sequence of actions to be taken to reach that location? And, well, you humans used to be able to do it before smartphones. I mean, of course, robotics has been focused on the problem of navigation, which is very narrowly defined as building maps, and then localization in those maps, and then path planning in those maps. But the approach that we are taking to navigation here is slightly more general. It's essentially all about taking whatever stimuli we can and being able to construct some representation of space where the agent can situate itself and then reach its destination. And there are lots of adjacent questions to be asked. For instance, if we are navigating, we want to know where did we start in order to be able to go back to the nest. Also, how distant is our current location from the goal? Or what is the shortest path? And that can be done using a graph, a map, but also without maps. Have I been there before? A very important question for loop closure, and essentially the fundamental question that's asked in robotics when building maps, before doing bando adjustment in simultaneous location and mapping. And finally, the question that we all ask in a car after a long ride, how long is it until we get there? Are we there yet? So, as I said, we are going to use deep reinforcement learning. And the different 5 papers, which I'm going to explain, are chronologically investigating 4 different themes revolving around navigation from raw sensory input. The first one is just the idea of exploration, exploring an environment and taking advantage of the multitask nature of that activity and of the multiple sensory inputs. The second one is about trying to study and learn a representation inside the neural network of space and relate it to what has been observed in neuroscience in the cortex of mammalian brains. And here I'm going to detail our Nature paper on learning representations of grid cells emerging once we train a neural network to predict its position. Then we are going to attack the problem of generalization to new environments. In this case, it is essentially one-shot learning, which means the agent is exposed to an environment it hasn't seen before, and it finds the location of a goal, and then once it responds somewhere else in that environment, it manages to find the shortcut to the goal. So basically to build up rapidly a representation of that space in order to use it for planning. And finally, and that's the question on which I'm working right now, it is incorporating all those techniques with real-world data. The previous work has been done in simulation, and I will detail what kind of environments we have been using for that. But in the latest work, we have been using Google Street View images to train navigation agents, as well as images coming from a campus of a university. So, as I said, deep reinforcement learning is the fundamental algorithm what we use. And that algorithm supposes that we are taking observations from an environment. Here, that environment is a three-dimensional game. And the observations consist in two-dimensional pixel images. Those observations are necessarily only partial. So it's a partially observed decision process. We can't see what's behind us, basically. And the agent, which is a piece of neural network software, is taking those observations in. And it also has a goal which is specified to it, and it has to maximize the goal. The reward structure that we use in this case is basically giving high points if the agent reaches a goal, and smaller points if it reaches some intermediary rewards, like we place some apples and coins throughout the labyrinth to encourage the agent to explore. So the agent takes observations. It can act. So essentially make a prediction over a finite category of actions. And it gets reward for that. And we can see, this is an illustration coming from a paper published by Max Jaderberg, Vladimir, and Wojciech Czarnecki. One of the two papers that introduced deep reinforcement learning with navigation and auxiliary rewards. The other one I'm going to present. And in this paper, the agent was trained with 84 by 84 pixel images coming from a three-dimensional environment called DeepMind Lab, which is loosely based which is actually based on the open source version of OpenArena, which is quake-free, sanitized. Voilà. And the agent essentially is only picking apples and trying to go to the goal. The agent contains a convolutional neural network processing the 84 by 84 images. And you can see the activations in the first and second convolutional layer of the neural network, and then in the fully connected layer. It also has a recurrent neural network, in this case, a long short-term memory, which enables it to accumulate evidence over time. And finally, that neural network makes two different types of predictions. One is a prediction of a policy of possible actions. And the final action is sampled based on that probability predicted by the agent. And the second prediction is the one of a value function, which can essentially be described for those less acquainted with reinforcement learning as an estimate of future rewards. In addition to the standard reinforcement learning architecture, what this paper introduced, and what we also introduced in our study, was the idea of making constant estimations or predictions about the environment. And we did that in order to add more information for the agent to exploit. So let's deep dive into that paper, which is called Learning to Navigate in Complex Environments, which was published at iClear in 2017. So one problem of navigation is that the goal can be located pretty far away from the starting position of the agent. And just a random exploration might not necessarily lead the agent to reach the goal position. So a possible workaround is just to place some intermediary rewards, such as apples, that yield a smaller number of points, but encourage the agent to go out places to get those intermediary rewards. And hopefully that agent will reach the final goal. However, that may seem unsatisfying. The other approach is maybe to make the agent do constant predictions about its environment. And in this case, we've focused in our paper on predictions about, that are related to the geometry of the environment. The first kind of predictions we were making was the depth field. In the case of a three-dimensional game, they all come with a Z buffer, essentially an estimate of how close things are when the image is rendered in 3 dimensions and projected onto the screen. And this is not completely far-fetched in terms of navigating agents. After all, humans benefit from stereo vision, which enables us to see how far things are. Rats have whiskers, which we can use for sensing close obstacles. So we used depth prediction as one of auxiliary tasks. The second auxiliary task, which we introduced initially and then discontinued later, was basically predicting if the agent is stepping back on its own footsteps. So here we can refer to pheromones left by an animal walking around. Well, it was an idea we investigated, but we focused at the end only on depth prediction. And those auxiliary tasks ended up being extremely helpful, not only for learning the navigation policy, but also for learning a presentation of a space. Let me maybe show first how this all works. So in this video, I'm going to show successively more complex environments in which the agent is navigating. The first one is inspired by the T maze used in neuroscience. We call it an I maze. The goal is always hidden behind one of those 4 arms. And the only way for the agent to reach it is really to go all the way until it can see the goal. And you can see in blue that the agent tried 3 arms before finding the final one where the goal was located. And then, as it respawned, it exploited that information and kept going back. And at each episode, the location of the goal was randomized. So the agent had to basically memorize the position of the goal. In this case, the agent is navigating in a much more complex environment. We call it a large maze. And the goal is, I think, randomly placed as well. And what's interesting, no, sorry, it's static. So this goal is always placed at the same location. So here the difficulty for the agent is to basically localize itself when it responds during an episode. And I am plotting the decoding of a position, which essentially is an estimate by the agent of a distribution of the possible positions in the maze of where it is. And that estimate initially is very imprecise because lots of locations look ambiguous. But then, as it accumulates evidence, it narrows down the prediction. And finally, now I'm showing an agent navigating in a larger maze with a randomly placed goal. Here the agent, I think, found the location of the goal the first time, and then it being respawned somewhere else in the maze, and it's trying to come back to where it thinks the goal is located. It's not behaving in an optimal way, but it kind of works. And what I was showing a little bit earlier was that the agent kept making predictions of a depth field. And what we called about predictions about depth was basically a prediction of 4 by 16 image with each pixel corresponding to the distance, average distance in that area of the image to elements of the maze. So we considered different sizes of mazes. The I maze with randomly placed goals, and small and large mazes with static and randomly placed goals. And what we were able to achieve in that study was a good behavior of the agent in small mazes where it could consistently return to the goal, even if that goal was changing position at each episode, and relatively good exploration strategy in a larger maze. And if you wanted to replicate those experiments, you can use the DeepMind lab environment, which is available on GitHub. So what was the architecture of the agent? We considered as a baseline the simple convolutional neural network, the same kind of agents that were used in the first paper on playing Atari games. And basically, it only had 84 by 84 inputs sent to a convnet, predicting the value function and the policy. Then we used a more complex baseline involving a long, shorter memory recurrent neural network. And the training algorithm for this was a specific flavor of reinforcement learning called advantage actor-critic reinforcement learning, paper published by Vlad in 2015, which basically enables to do parallel training in a distributed fashion over a large number of actors, each playing in the environment and then backpropagating the gradient through the neural network and then sending updates to a centralized parameter server. This enables essentially for the agent to experience a large number of games at the same time and to both provide some randomization and also to just increase the speed at which it's training. So the reinforcement learning works in the following way. The agent observes a state S, which can basically summarize the images which are seen by the agent. And it takes an action A. And every time point, it makes a prediction of a value function V, as well as of the policy pi. And it updates the policy and the value function based on the gradient of the policy, which has two components, the log of a policy and the advantage function itself, which can be seen as the difference between the actual sum of discounted rewards, and those rewards are discounted exponentially, just like in finance we discount exponentially future returns, plus the rewards, the value function that will be observed in k steps, also discounted, minus the current value function, which is why this algorithm is called the advantage actor-critic. And the value function itself is trained to be, the current value function is trained to be predictive of the discounted rewards and the future discounted value function. And this is the whole policy term, which contains the advantage function term and the gradient of the log policy. And this loss function is optimized to optimize the parameters of the neural network. So we looked into adding additional auxiliary rewards, auxiliary functions to help training the agent. And I was talking about predicting depth. So in order to be able to do that, we had to modify a little bit the architecture of the agent. So starting from the convnet and recurrent neural network, first of all, we added the current velocity in previous actions. And then we added a second recurrent neural network so that the policy itself relies on some hierarchical architecture where the first recurrent neural network would be used to have the agent make associations between rewards and images. And the second recurrent neural network would take advantage of that accumulated evidence to make predictions. And both stages of the recurrent neural network had auxiliary tasks. In this case, predicting depth. We tried quite a lot of combinations of hyperparameters and architectures. And we tried, for instance, placing depth prediction only on the first LSTM or on the second LSTM, or not at all. And essentially, we noticed that if we place auxiliary rewards pretty further on, auxiliary tasks pretty further on in the architecture, it helps train the entire architecture. And the motivation for adding those extra tasks is essentially to create more sources of gradients coming into the neural network. The problem of reinforcement learning is that the rewards are very sparse. So you have only a single scalar providing your gradients. If you have a constant estimation or constant prediction of auxiliary information, then you have so many more gradients which can be used to optimize the system. And this essentially helps us speeding the neural network. And you can see that the baseline, the feed-forward neural network in red, and then the plain LSTM and convnet are outperformed in terms of reward, both at the beginning and also in the final result when we add auxiliary tasks. More interestingly, we considered not using depth as a target for prediction, but actually as extra information given to the network. And that was not as optimal as having the network predict depth. And we hypothesized that basically, if we give a depth as information to the network, it may not actually take advantage of information, whereas if we force the network to make the estimation of depth, then it needs to learn representation that is good both at navigating and at predicting depth. And basically, also that's how it gives all those extra gradients. We were able to achieve a form of meta-learning, learning to remember where the goal is located in small mazes, not in larger mazes. And I also added this task of decoding the position of the agent. And this was done by essentially having a sort of non-invasive inspection of the state of the agent by placing a multi-layer perceptron, classifying the position of the agent, but stopping the gradients between the rest of the system and that predictor. So this way I could always keep training the system based on the current presentations, but not modify what's inside the neural network. And this was very useful for basically inspecting what's going on in the neural network. So we can see that when the agent spawns, it has a very bad estimate of its own position, but as it accumulates evidence, the predictions of its position are much more acute. This study had two limitations. The first one is that we're not able to memorize a randomly placed goal position during a new episode in a large maze. And that was due to the architecture that we used. And the second one, that we didn't really carefully consider what kind of representations can be obtained inside that agent. So this was motivation for our second project, which was published a few months ago in Nature, where we linked the training of a navigation agent to neuroscience of what happens in the mammalian cortex. In the 70s, John O'Keefe and Jonathan Dostrowski discovered the so-called place cells, neurons which fire in a rat when the rat is at a specific location in a small enclosure, irrespective of the location. Irrespective of the direction. So for the same location, but irrespective of the direction, those neurons fire at that specific location. And they depend both on visual stimuli and also on olfactory stimuli. Later in the 90s, other neuroscientists discovered head direction cells, a sort of an internal compass representation in rats. And in 2004, 2005, 2006, papers had been published by a graduate student, Finn, and the two advisors, Edvard and May-Britt Moser, about grid cells, in which case neurons would have a constant firing activity whether the rat was at different locations of the maze, but always on a regular grid. So for instance, one set of grid cells would fire if a rat would be here, and there, and there, and also here, but not in between. And those grids would be defined by a scale and by an orientation and by an offset. And they have hypothesized that those grid cells can essentially be seen as a sort of Fourier transform decomposition of space. If you combine multiple grid cells, you actually can predict the location, and they are connected to place cells. So the place cell system is the cognitive map, and the grid cell is used by rats and has also been observed in humans for help in localization and short-range navigation. So this video maybe explains in a better way what I just said. It shows an agent or a rat moving around and the locations of a firing of a specific cell. So this can happen at different scales for different sets of cells. And combining the activity from multiple scales can be used for determining position. So the hypothesis that we wanted to test is that if we combine linearly grid cells, we can obtain place cells. The way we did it is that we trained agents to predict position, and we placed a linear layer in between this position predictor and something else, and we looked at what's happening in that something else. So what we trained the agent for is path integration. So if you have studied robotics, path integration is basically accumulating velocity over time. So as the agent, a rat, moves around, starts from a starting position with a start orientation, theta 0 and x0, y0. It moves around. It ends up in a different position at time t. And at time t, it also has this current angular velocity, as well as a forward velocity and a sideways velocity in egocentric reference system, uv. We can use a closed-form solution to integrate consecutive velocities to keep updating the absolute reference, absolute coordinate system position of a rat, theta and x and 0. Theta, x, and y. So what we trained the neural network to do was basically just to accumulate velocity in egocentric coordinates to predict global coordinate system position. And we did that using just a plain recurrent neural network, and we started working on that in 2005. So the recurrent network will get the velocity inputs, as well as the original direction and position, which we used, instead of using x, y, and theta, we used a different representation called basically grid cells and place representation. I'm going to explain you exactly how it looks like in a second. And that network was trained to keep making predictions of the current grid cell, place cell and head direction cell representation at every time point. And what we looked at was the activity of the hidden units of a recurrent neural network before a linear layer that makes those position predictions. So the place cells themselves were defined as Gaussians. So we just scattered some Gaussians across space, because place cells essentially can be modeled as Gaussians sampled across a two-dimensional space. And for head direction, we used an equivalent formulation, which is the Gaussian with angles, so it's the von Mises distribution. And in order to be able to obtain this representation, all that was enforced was some level of sparsity, and which we obtained by using dropout. 50% of the inputs to the linear layer were silenced at any point, so this forced the neural network to have an optimal presentation. And there was also some gradient clipping applied to this. And that was it. Using just this very simple architecture, integrating velocity in egocentric reference space to predict position in global space using these Gaussians of place cells and head direction cells, enabled us to obtain this kind of representations, which matched what is obtained in what has been obtained in literature in neuroscience for the past 10 years. So on the top, you can see rate maps, which is the activity of a single unit of a neural network across a two-dimensional space. And you can see that the first unit acts most strongly on different locations, which could be characterized as lying on a hexagonal grid. By the way, if you wonder why a hexagonal grid, the simplest explanation for that is that if you try to pack circles of equal radius in a two-dimensional space, the optimal configuration is having one line of those circles, and then another line shifted by half, and then again. So basically, it's an argument of optimality for a given unit or a given grid cell. And what we notice is that units that exhibit this grid cell-like behavior, of this, at least this hexagonal pattern, were invariant to the rotation or to the orientation of the agent. And we were able to actually characterize that these corresponded to grid cells by computing spatial autocorrelograms across space. So this map basically shows for different displacement the correlation of the activity with itself. Other units were shown to be specific to orientations, and they didn't display this same spatial regularity. So we could hypothesize that those units were essentially head direction cells. And there were also another set of units that could act as place cells or boundary vector cells, so basically predicting that the agent is close to a boundary. And these metrics were actually confirmed with the metrics obtained in literature, which is why the paper was ultimately approved by neuroscientists and the community. So this was what I just showed before was a very contrived example where the neural network was only integrating velocity, but had to be fed, had to be reinitialized with estimates of its own position. Instead of doing that, we could also do something else, which is feed visual information to the neural network and use that visual information to initialize the position of the agent. And so this was done using a convolutional neural network that could see from time to time images, because most of these images will be set to black. And this would act as a sort of a reset for the position of the neural network. And again, the same activity was displayed. So at this point, it was time to use it into a navigating agent that will be trained with reinforcement learning to actually go places. So the way this was done was by taking a pre-trained grid cell neural network, what was trained only in a supervised way, and then using it as an input to another LSTM trained with reinforcement learning to predict a policy and a value function on tasks involving navigation. And there is one extra thing that was done here, is that we wanted the agent to be able to remember the position of a goal. So the way we achieved that was by letting the agent go around the maze, and then once it would reach the goal, we would literally copy-paste the values of the hidden units of the grid cell network, keep it aside, and then when the agent would respawn in the maze, that extra copy would be provided to the LSTM. So basically at every point of time after respawn, the agent would know, because of the grid cells, where it is, but it would also have representation of where the goal was when it reached it. So it could basically start doing some sort of comparison between its current position and the position of a goal. So we basically created a sort of memory for that agent. And that was done in a very ad hoc way, but it did work. And we were, for instance, able to show that we can even train a linear decoder that would take those two presentations. Where am I? So the current grid cell activity. Where was the goal? Where am I going? And predict, using a linear regression, the direction to the goal and the distance to the goal. So essentially that grid representation ended up encoding a Euclidean metric of a space. And it was also useful for finding shortcut behavior for the agent. So in some of those mazes, there would be goals which would keep opening and closing, and the agent would discover where the goal is located. Then the door will be closed, and so the agent had to plan around the closed door, which assumed that it had figured out, in some cases, a shortest path behavior to get there. And that study actually did win the approval from the original authors of the grid cell paper in 2006, who received a Nobel Prize along with John O'Keefe for the work on place cells. So I talked so far about presentation, but I mentioned memory. And so far, for memory, we just had a hack. We would just make a copy-paste of some presentation of the agent at go position to use it later. This work, which was conducted by Greg Wayne and published on arXiv, was essentially about one-shot learning and memory in episodes where the environment will always be randomized at each new episode. And it would be all about predicting the goal location. So this architecture relied on two ideas. One of them is learning good presentation, and Loic will present a bit later sequential variational autoencoders, which were used in that study to build a good presentation of images and space. The second component is called differentiable neural Turing machines, differentiable neural computers, and it's essentially a read-write memory. So just a giant array, which follows the last read unit principle. So it just keeps being overwritten consecutively during an episode, and the addressing is learned. So it's just a neural network that works by an addressing mechanism by comparing a query and a key, which is stored in that memory. And the addressing works both for the write operation and for the read operation. And you can imagine that the way this worked here is that this network had to train itself to memorize the presentation of space, to learn how to write them in that array, and then when it would go around the maze, it would always keep making a comparison between the current presentation and what is stored in memory. And this way it could retrieve a previously stored bit of information and also retrieve additional information about, let's say, how to get there. And so basically that agent combined those two ideas. I'm not going to go much more into the details for that specific paper. I'm just explaining those two main ideas of how it made it work in a new environment. The paper is, the architecture itself is called MERLIN, Memory-Enabled Reinforcement Learning and Inference. The paper is Unsupervised Predictive Memory in Goal-Directed Agents. And I think the most interesting is just to show the behavior in navigation. So when an episode starts, the agent is just exploring, and the value prediction is pretty flat. It has no idea where the goal is, how far it is from the goal. And then once it finds the goal and it responds somewhere else, it consistently returns to the goal position. Bear in mind that this environment is new for the agent, so the specific configuration of rooms is different from what the agent has seen before. So it had to basically learn some presentation of space that is constantly changing and learn to store a position of the goal. Okay, we've seen quite a lot of work in simulation and even methods that are able to memorize in a one-shot setting. However, the simulation has some major limitations. Basically, even if it's partially observable and if it's a good model of a complex problem where information has to be accumulated over time, it's basically completely not real and doesn't correspond to the distribution of images you can see when you learn a navigating agent. So we decided to change the environment, and that's what we came up with. No, it's a joke. We used Google Street View images in order to work in the real world. So in this paper, which is going to be published at NIPS and which has been on arXiv since March, Learning to Navigate in Cities Without a Map, we replace the simulated environments and very structured mazes with photographic images coming from Street View and a structure that still follows a graph, but that graph can correspond to the layout of actual street maps. And we call that environment StreetLearn. It consists of panoramic images stored as equirectilinear images. Basically, you can imagine that it's like a Mercator projection inverted, or just, no, actually, no, a Mercator projection, actually. And with each view obtained using projective geometry from that specific panorama. So we decide to go for views that are 60 degrees field of view horizontally and 40 degrees vertically. And again, 84 by 84 images, which is still enough to distinguish objects on the image. And the action space of the agent is 3 kinds of movements. Turn left in the panorama by a fixed set of degrees. We use, for instance, 11 degrees. This way, if you need to turn multiple times until you actually fall back on your footsteps. And also, the agent can move forward if it is facing an actual traversable area. So it will never walk into a building or onto the sidewalk. And if it takes a decision to move forward when it's facing a sidewalk, it's just a weighted action. And the environments that we considered were New York, London, and Paris. Basically, I chose those environments because it was practical for me to debug the system, because I knew those places. Each of those contained between 15,000 and 60,000 panoramas. So for instance, the central London environment was 5 kilometers by 5 kilometers and 25,000 panoramas. And yeah, and we use those environments to actually define a multi-city data set. The task was very simple. We called it Courier. It consisted in giving the agent a destination, latitude, longitude, and images of what the agent sees at the moment. And that's it. We didn't tell the agent where it was. It had to figure it by itself by learning associations between images and latitude and longitude at reward time, when it would actually reach the destination. So it was a long learning process, obviously. We considered a different presentation, which was inspired by the place representation, which was dropping some pins on the map. So basically, I handpicked places I liked. And each of those places would define a Gaussian. So instead of describing a destination as latitude and longitude, I would describe a position as 0.5 Shard, 0.4 Borough Market, 0.3, no, that doesn't sum up, 0.1, sorry, London Bridge Station. And that essentially means somewhere halfway between the Shard and Borough Market, but not too close from the tube station. And these were provided as inputs to a goal conditional reinforcer learning for the agent. And the other input was just images. And that was a problem, as it was defined. So the agent would have 1,000 step episodes. It would be given a goal. If it would reach the goal, it would be given a new goal, and so on until the end of the episode. And in the environments already defined, it might have taken up to 600 steps to go from the furthest corner of the map to the other corner, assuming that, let's say, the agent would spawn at London Bridge and had to go to Regent Park. The architecture was very simple. We considered baseline, just a convnet and LSTM, with an additional goal, so a modification of the classical agents. We also considered the city navigation agent, where we introduced a second LSTM. I like those hierarchical architectures, as you can see. And that second LSTM was making an auxiliary prediction of its current heading. So basically, the agent had to learn a compass function. And the reason for having that extra LSTM will be evidenced a bit later, in 2 minutes, when I explain how we adapted the system to multiple cities. Obviously, the training was very difficult, and the only way to actually get this agent to learn the task was by using curricular learning, which means that initially we would start with the agent having the goal being very close to the position of the agent, to the current position of the agent, let's say 500 meters. And once the agent would master that task, we would just anneal the goal to be sampled further and further away, up to 5 kilometers. And that worked. And it had this very satisfying human prior to it, I would say. And we managed to train those agent architectures in other cities. These are the results obtained for New York. The behavior was not optimal compared to an oracle that would know exactly the shortest cut behavior to get to the goal. But it still worked. And of course, it was much better than any heuristic that used, that didn't know where the goal was, but would still navigate forward along streets and then try to take left and right turns. And the architecture that we introduced, which was making those extra heading predictions, worked the best. In central London, which was slightly more difficult than the smaller environment of NYU in New York, you can actually see the curriculum. The first phase is the goal being 500 meters away. Then we move the goal further and further away, and so the rewards actually starts dipping, because during one episode, as the goal gets further and further away, the agent cannot get the same reward, because it takes more time to reach the goal. But then once the curriculum is finished, and at 5 kilometers, the agent continues learning. And another video showing the agent navigating in Paris. You can see the destination in red. So yes, I would like to emphasize the fact that the images, just like on Google Street View, had faces and license plates blurred. And yes, and this is, of course, a trained agent that has an optimal behavior. And the same behavior in London. So, of course, at this point, you might be thinking that the agent is essentially learning by heart a map of Paris and London in an indirect way. It never has access to the two-dimensional representation, but it needs to learn something by making these associations in the images and destinations. So we investigate a little bit within the definition of a problem, the issue of generalization. So the way we did it, as you recall, the goal could be defined as latitude and longitude. And what we could do would be to separate some areas of a training data set which would be traversable with the agent. We wouldn't stop the agent from entering those, but we never sample the goal from there. And because the representation of a goal had a little bit of linearity, at least locally, we're hoping that if we pick a goal destination within those black areas, the agent would still be able to reach those. And it did work when the grid of left out areas was pretty dense and each area was pretty small. So the agent was able, to some extent, to generalize to goal positions it never saw by using interpolation of representation of a destination. The other kind of generalization that we're interested in was what would happen if it would take the agent, train on some cities, and then test it, or at least retrain it on a new city. And the problem is that our formulation of a problem implicitly associates latitude and longitude to images. But what we can do is to basically freeze the convolutional neural network and even freeze the policy, LSTM, and just have an interchangeable per city specific LSTM that associates the goal to the images. And we observe that does work, provided that we pre-train the system on a lot of different cities. We can then add a new city, so a new component to the neural network, and keeping the convnet and LSTM frozen. So essentially that extra LSTM has to adapt to whatever policy interface there is and whatever visual features there are already pre-trained. And so that did work. And there's another video here in New York. But I decided to add, at the last minute, this fifth paper written by Jacob Bruce, who is currently doing an internship with our group at DeepMind, who tried to replicate our study at his university, at Queensland University of Technology in Brisbane. Not using Street View, but basically building a Street View by himself. And he was interested in the problem of generalization. What he did was to just run a robot around in his campus. And the robot was a Pioneer robot. He acquired those panoramic images. So the input to the agent would consist of fully panoramic images. So it was maybe slightly simplified. The action space would still be the same, turn left or right by 90 degrees and move forward. And most importantly, he trained using data acquired over a few hours only, and used those data to define an interactive environment that could be explored billions of steps by a learning agent, but the data acquisition itself took a few hours, which I think is the most important consideration for reinforcement learning. It's so much, the problem is not that reinforcement learning takes a lot of steps of gradient descent, it's that it needs lots of data. Here it's only a few hours. And then the test data were different. Well, it's the same location, but on a different date. And it worked. So yes, the test data had changes in sunlight, weather conditions, shadows, people, obstacles. Yes, another trick that he used was to basically start on a pre-trained architecture. And he was happy to report that, well, compared to an untrained neural network, the pre-training on ImageNet definitely helped. And also the agent was able to achieve a navigation, goal-driven navigation behavior. These are examples showing on the Oracle path and what the agent would do on training data and what the agent did on test data. He only tested 11 trajectories because each of those trajectories involved him sitting next to the robot and basically receiving an instruction from the agent and then pushing the button, okay, forward, left, okay, yes, it works, forward. And only one trajectory failed, didn't reach the goal. The other trajectories worked out, maybe even if they were not optimal. And that concludes this presentation. Thank you very much. So these are the 5 papers which I discussed. If you have questions.
I think you should have microphones, by the way. Yeah.
Yes.
Well, thank you very much for a very informative and interesting talk.
Thank you.
You mentioned that this curriculum learning was really important
Yes.
to the agent's success. So I was wondering if you tried any other exploration methods or if you tried some automated curriculum learning.
Yes. So the first thing we tried was to basically add intermediate rewards by having a cone of. So in our setup, the goal was defined as an area of radius 100 meters, which is not huge compared to the full area, which was 5 by 5 kilometers. And then an extra 100 meters, so to 200 meters total, where the reward will be decreasing. So the agent basically, it's a bit like when somebody drives you somewhere, and just before you reach your goal, you start telling that person, okay, we're almost there. So that started 200 meters before. And this essentially was equivalent to having a visual indication of what the goal looks like. Yes, because we didn't have that at all. Yes. We tried by having this radius 500 meters, and that did make the agent learn, but of course, it becomes a little bit unsatisfying. We tried just adding apples or coins or whatever we call it. Didn't work. And that's it. And now, yes, we could have a population-based training with an adaptation of curriculum, but we didn't go into that. We just used a bit ad hoc curriculum. Yes, but that's a good exploration idea. Yes?
Thanks very much for the great talk. Just one question about that auxiliary learning that you did. So in the grid world, you had this velocity to position
Yes.
auxiliary network. Then in the city scenario, you switched to compass.
Yes.
What was the rationale for that? Is it that you have to place too many Gaussians on a city map, or
Yes.
and second question, how did that compass function help you generalize to different cities?
Yeah. So I didn't include the slide that shows results without compass. It still works. It just doesn't work as quickly. It doesn't train as quickly, basically. So, but we still managed to train the system to solve that task. So it's essentially about adding gradients. And now the choice of the place, we used place prediction only in the place cell paper, in the grid cell paper, because there was this intuition about predicting constantly the position of the agent of a mouse in using place representations. We didn't use it anywhere else. And we tried other auxiliary tasks, but you can actually do auxiliary rewards, reinforcement learning based, which is predicting the neighbors. So which parts are traversable. It's like having a LiDAR scanner, a LiDAR range scanner on the car, telling that you can go forward or not. Yes. Have I answered your question fully?
The second question about how that compass function helped you generalize to different cities. You mentioned something that...
I think that instead of having to generalize, it's actually doing the reverse. It's learning an association between each image and the heading of it. Yes. So we would probably need a different function to generalize. Maybe the one where you predict the neighbors. I had a question over there. Yes.
Thanks. So I saw that you used two different CNNs in the grid cell paper. So one for the grid cell network
Yes.
and one for the policy network. So were the representations for the two significantly different?
Yes. So the first CNN for place cells, for grid cells, had this trick that we used of basically blinding the network 90% of the time. And that essentially would force the network not to memorize position based on images, but just use like a reset from time to time. Yes. The other one was not blinded. And it was basically easier to train a different one from scratch. But it could be the same. Yeah, it was easier in that case to just train a different one. Yes.
Okay, thanks.
Can you just do one final question?
Yes.
So place and grid cell firing is locked to a theta rhythm. I believe as you run into a place cell, you fire at one phase of the rhythm, and as you run out, it fires at a different phase. Has anyone looked at correlates or analogs with that in deep networks?
Not that I know of. Yes. There are, well, the other people at DeepMind who looked into that, Kimberly Stackenfeld, she looked into success representations in the context of reinforcement learning, but it was not specifically on theta waves.
All right. Thank you very much.
Thank you.